Okay, so now that we sort of understand what's going on here with these polynomial models, how do you actually specify D? So how do you specify kind of what degree of polynomial to fit your model to? So there's kind of two ways to do this. The first, and this one is likely what you would do if you were doing inference. So what that means is if your primary goal was to sort of talk about the relationship between a specific x and y variable, then you might pre-specify D before looking at your data. So you may pre-specify that you think the relationship is a certain way, and then you would test whether or not that hypothesis was true. And that would be basically the end of your analysis for that, if inference was your goal. If prediction is your goal, then you're really trying to kind of find the best model fit to the data at hand, of course, taking into account that you might get a different data set and might want to sort of balance between this bias variance trade-off. And so for that, for prediction, you would use cross-validation to pick D. And so why is that? Well, because as your D is increasing, if you're just picking it based on your training data alone, you're going to, as we've seen, you're going to fit a very, very, very flexible model, and it's going to do a great job eventually basically connecting the dots between your training data. But of course, as we've talked about this whole class over and over again, the real goal here is this bias variance trade-off, where we don't just want to overfit our models to the training data, but we really want to sort of account for what would happen if we saw some new data from the same population. And so that's what cross-validation lets us do. It lets us kind of balance between that bias variance trade-off. So polynomials have notoriously bad tail behavior. And so what that means is that they can be bad for extrapolation. So kind of as you get out into the tails, if you were trying to guess or predict a new value, a new y value for a given x value, it can be pretty off. So what does this mean? Well, essentially this means that you want to be really careful when you're doing polynomial regression, especially when you're including higher order polynomials, kind of when you're anywhere sort of out in the tails or on the edges of your x values, because it's going to be kind of easier and easier for that model to sort of do a bad job or overfit your data. And so there's a couple ways that we can fix this with some other techniques that are maybe a little bit less flexible and not so bad in the tail. So we're going to talk about that. Briefly, another way to create a transformation is just to cut a variable into distinct regions. And so this is known as a step function. And so what I've done here is, instead of fitting this kind of flexible model that connects these points, instead I'm fitting a model with just indicator variables across each of these three steps in this case. And so here I have an indicator variable that x is less than 35, and so that's going to be this first step here. And so if I'm predicting a value, a population value when x is less than 35, I'm going to end up here at like 1200 or so. So for any new value, any new age less than 35, I would predict having a population around 1200. And of course, this is not going to be super accurate because it's going to basically underestimate these points up here and overestimate these points down here. But it kind of, the closer and closer you make these steps, and the closer you get to sort of refitting that polynomial type function. And then the second step here is going to be between 35 and 65. And so for that, I've got this line here. And so something around maybe 400 or so is what I would predict for people for the age between 35, the population for the age between 35 and 65. And because these points are a little bit closer together, I'm getting closer to sort of having a better fit here. And then when I get all the way down here into this bottom tail, when I get to greater than 65, these points are all pretty close together. And so I'm actually doing an okay job with this prediction when I'm using this indicator variable down here. So the way you do this is you create dummy variables for each group, or indicator variables is another word for that. These are basically variables where it's going to be a 1 if the observation is in that group and a 0 otherwise. And then you include these variables in multiple regression. The big issue here is the choice for cut points or knots can be problematic and can make a big difference. For example, here's one step function where the one that I just showed you, where I chose my knots here, or my cut points at 35 and at 65. Here's another one where I chose my cut points at 15 and at 65. And you'll notice I get wildly different results, especially for the people here between 35 and 15. So in this model, I'm very accurate actually up here at the top, whereas in this first model, for those less than 15, I'm really not that accurate. But then, because I'm lumping in all these people who are greater than 15, but less than 65 together, I start being much less accurate in this range as opposed to what I'm doing with this initial model, where I'm a little bit more accurate in my second range. And so those knots are really important for sort of being able to determine accuracy. And of course, having more knots would make this more accurate. So the kind of next step here is, okay, well, instead of using the step function where I'm just connecting these steps via a straight flat line, I could do what's known as a piecewise polynomial. And so instead of having a single polynomial, an x over its whole domain, I could use different polynomials in regions defined by knots. And so this is going to be more flexible than what we've just saw with where I'm doing this like stepwise function. Here's an example of what that would look like. So I would have one model where I'd have this beta 0, 1, beta 1, 1, beta 2, 1, and beta 3, 1. And this first model is going to be if x is less than c, so less than some cut point or less than some knot. So I would fit this model on that data. And then I would have another model that would have the same number of polynomial terms, but that would be when x is greater than or equal to c, and so based on the other side of the x space. So what could go wrong here? Well, it would be nice to have some constraints. For example, it'd be nice to have continuity. So the issue here is because there's no constraints, you might have these big jump points right at C, right at your knots. And so that's where splines come in, which kind of blend this idea of being able to use those, the kind of piecewise, the idea of cut points, but also kind of incorporating polynomials, but including some constraints that kind of improve this. And of course, if we didn't include any constraints, because these are polynomials, the tails are going to have the same kind of issue that they would in our first case when we were talking about polynomials. And so constraints can improve those tails and also can improve the continuity and things like that. Okay, so here's an example to sort of show what I mean by this. And so in this first case here at the top, I'm fitting, in this case, I'm looking at age on the x-axis and wage on the y-axis. And here on the top, I'm fitting a piecewise cubic. And so what that means is my cutoff here, or my knot, is at 50. And so before 50, I'm fitting a cubic model, and after 50, I'm fitting another cubic model. And so what's going on here? Well, this model has no constraints. I'm just I'm fitting it exactly as it ends up. And so I have this big jump. So if you're exactly 50, I don't quite know what to do with you. I wouldn't know if we should give you this predicted value from this point or this predicted value right here. And more importantly, kind of there's this jump that sort of doesn't really logically make sense. There's nothing that would make you think that being exactly 50 would make you jump a certain way. And this is likely being driven mostly by the tail behavior of polynomials that we've talked about, how it can have kind of funky tail behavior. And you want to sort of constrain that a little bit. So this next example here is going to sort of do a little bit better, where this is a continuous piecewise cubic. And so it fits the cubic function here between each of these, but it has one requirement that basically there's a connection point between these two. So it gets rid of that jump. And so that's nice, but you'll notice there's this little dip here. It's not really smooth. And so that's where a cubic spline comes in, where it actually smooths over that knot location. And then just as another example, so you can sort of see what this looks like, a linear spline is another way to do this, where instead of, so a cubic is going to have the polynomial, there's going to be 3 polynomial terms or 3 degrees. Linear would be if you just included 1, so you just had the linear part of each model, but you allow for that to split depending on what side of a knot you're on. So a linear spline with knots at k equals 1 to k is a piecewise linear polynomial continuous at each knot. And so here's an example of what that looks like. And here our BKs are basis functions. And so this is going to be beta 1 times some function of x plus beta 2 times some function of x, etc. So beta 1 is just going to be x, and beta k plus 1 is going to be x minus this knot here. So this knot for k equals 1 all the way up to k for the number of knots that we have. And here, this plus here means the positive part. And so so in this xi minus the knot with a little plus sign, that's going to be equal to xi minus the knot if xi is greater than where the knot is, and it'll be 0 otherwise. So that's basically, this is the construction for how you would fit one of these spline models. And so this is what this looks like, just to sort of give you some intuition into what's happening here. But if this is f of x is some function of x, and we've got a knot here at 0.6, we could, if we were fitting the line like this, it would just be a straight line. But if we were fitting linear regression, but if we're fitting the spline where we basically have a shift at 0.6, this is what that shift would look like. So basically, after 0.6, we're fitting a different linear model, so that we're estimating the points kind of differently there. And this underneath here, this graph shows you, it maps that to a basis function. So you can sort of see the difference between this b of x, that basis function, as opposed to what the actual predicted values would be. So a cubic spline is going to be a spline with knots at k equals 1 to k, but it's going to be piecewise cubic polynomial with continuous derivatives up to order 2 at each knot. So it's similar to a linear spline, except instead of being a piecewise linear, it's a piecewise cubic polynomial. So again, we can represent this model with the truncated power functions. And so now these b's here are going to be basis functions, but now b1 is equal to x, b2 is equal to x squared, b3 is equal to x cubed, and any bk plus 3, so any basis function that's greater than 3, is going to be equal to x minus the knot cubed, as long as it's positive. If this x minus the knot is here cubed is not positive, if x is greater than the knot, then this is going to be what we stick in there, and if x is not greater than the knot location, then it's going to be 0. So this is what that looks like. And again, so this would be like the blue line would be if we were just fitting a polynomial function across this whole space. But we've got a knot at 0.6, and instead we're fitting a new polynomial here in this ladder space. And mapping that to what a basis function looks like, this is what it would look like. So a natural cubic spline has one extra constraint that's super helpful. So as I mentioned, sometimes in the tails, you can end up with kind of funky behavior with polynomials. And these splines, basically, they help on one side because they connect those tails together to make sure that you've got this continuous linearity there in the centers. But on the edges, you still have these tails that could end up having some bad behavior. And that's where natural cubic splines come in and are really helpful. So a natural cubic spline extrapolates linearly beyond the boundary knots. And so what that means, boundary knots are basically the final knots on either end. So like the first knot and the last knot. So this adds 4 extra constraints, and it lets us put more internal knots for the same degrees of freedom as a regular cubic spline. So here's the example where the blue line here represents the cubic spline. And you'll notice in the tails it gets kind of wiggly. And the red line represents the natural cubic spline, which is a little bit more consistent and therefore has better tail behavior. So one strategy, so this knot placement is really important despite the method that you're using, and we're going to mostly be using natural cubic splines from now on because that's sort of a preferred method, especially for prediction, but for inference too. So picking the knot placement, one strategy is to decide k, the number of knots in advance, and then place them at appropriate quantiles of the observed x variable. So a cubic spline with k knots is going to have k plus 4 parameters, or degrees of freedom. But a natural spline with k knots is going to have k degrees of freedom. And so this is another reason why natural splines are preferable, because as you increase your degrees of freedom, you're kind of necessarily increasing your flexibility. And so being able to sort of constrain that a little bit can help with the parsimony of your model and this bias variance trade-off and avoid overfitting and things like this. And so here's a comparison of a degree 14 polynomial and a natural cubic spline, both of which have 15 degrees of freedom. But if you notice the natural cubic spline in red, basically those degrees of freedom can be used to sort of account for a little bit of wiggle in the data, but they're not being overly emphasized in the tails because it has this nice constraint that it's linear in the tails. Whereas the polynomial is really going crazy, and especially down in this tail, anyone that has a age over 80 is basically being predicted eventually to have a wage of negative infinity, because this polynomial is going to go all the way to infinity, which is obviously not sensible. Whereas if we look at the cubic spline for prediction, if we get over 80, it sort of keeps it in a sensible range.